Okay, so welcome to lecture 2 of quantum mechanics 1. So this is today will be lecture 2. So before I start, are there any questions from either the previous lecture or from the tutorial?
No, sir.
Or any question in general?
No, sir.
I have a question. Like the black body is, should it be necessarily black in color, or any color would do?
Yeah, that's a good question. It doesn't have to be black in color. What is important here is that in some sense it's an idealization. Okay, so the ideal thing should be black in color because uh, why are we calling it a black body? Because it is supposed to absorb all the radiation that is incident on it. So experimentally, what do? We don't actually have to color it black. What we do is that we have to create a cavity with a very small, uh, entrance through which radiation can go into the cavity. And because of the geometry of the body, the radiation will basically bounce off several times. And of course, at each bounce, there is a non-trivial probability that it'll get absorbed. So because the radiation cannot get out very easily, very most of the time, for overwhelming probability, the radiation will be absorbed. So even though we call it a black body, it doesn't have to be exactly a black color. The way we are constructing it ensures that all the radiation is absorbed. Okay.
You mentioned when the radiation is incident on it. So does it mean if it falls from angle, it can be reflected?
No, I mean incident as in something that falls on it. That's what incident means. So in this case, incident means that a radiation that enters the black body through the little aperture. Okay. So let me just draw a picture. I think that'll be easier to explain. So you know, what we are considering as a black body is the inside of this object. Okay. So we have some box, and it just has to be large enough. And there is a little aperture. So and what will happen is that for most of the radiation that goes in, you know, it won't get reflected. The angle of reflection will be such that it won't be able to get out, right? So it'll be something like that. So so after a few reflections, it'll get absorbed. Okay. So by incident, I mean it's going to be very, very unlikely that the radiation is going to leak out. Okay.
Understood. And another question is about the shell you considered on the number of degree of freedom, the shell with
Yeah.
thickness dn. So what
Yeah.
what what did we do with that thickness of dn? I mean, what was the goal of doing that
Oh, yeah.
shell thing?
It's just it's just what we do when we are trying to uh, compute the volume, right? You suppose you saw that in physics 112 or electrodynamics, you know. So we have a space, and what we're trying to do is we're trying to count the number of points of integer points in that space, right? So you know, essentially what we're doing is, so let me give a lower dimensional example that'll be easier. So for example, if I have, say, a two-dimensional plane, and this is, say, the x-axis is an x and ny, okay? And so what is this? This is basically the points, it's a lattice, it's a square lattice. All the points for which nx and ny are integer, right? And in all direction. So if I take n, x and ny to be very, very large, so I'm just zooming out. So this is nx and this is say ny. And suppose that around here, the value of nx is about 10 to the power 10. I'm just exaggerating, but very large. Here is 10 to the 6 or something, right? So here, so if I take a small interval here, say dn is much, say, smaller than nx and ny, right? So essentially, we can consider delta n to be, at this scale, we can consider, because delta n is so much smaller than nx and ny, we can, consider these guys to be continuous variables, because because nx and ny is so much larger than 1, and we know that the distance between subsequent points is essentially 1. So then what we're doing is that for large values, we are counting how many points there are between two concentric shells, right? Because as concentric circles. So let me draw better circles. So they're actually concentric. Well, this will have to do. So okay. So we want this. Okay, let me do this again. Okay. Right. So because there's 1 point per unit area, if we just calculate the area, we will be counting the number of points. So now the question I want to ask is that, what is the area of this shell? Well, it's going to be the radius of the circle. So if this is, say, n, then it'll be 2 pi n, and then this thickness, which is delta n. So this is going to be the area. Then what is going to be the volume of the whole space? It's going to be this object integrate from 0 to infinity, right? So we're just doing a higher dimensional analog of this. Of course, there is near this region, near the origin, this approximation that, these are all continuous variables. This is not an accurate approximation. But the overwhelming contribution to this integral is going to come from large values of n, right? So we can justify this this sort of approximation.
So why is the limit infinity?
Because you can there is no ultraviolet cutoff, right? You can have as many wavelengths as you like inside the cavity.
So the dots of the graph are wavelengths.
Yeah. Number of wavelengths that you can,
okay.
Yeah.
So, and how is this related to modes? I mean, what did you?
These are the modes, right? These are the modes. We are considering each of these the modes.
Okay, got it.
Okay. All right. Any other questions from anyone else, or?
I have a question. I mean, I posted that article on class discussions about the way someone else calculated the density of states and all that.
Okay, good.
They did two things differently, which I think in our calculation canceled out as well.
Okay.
And firstly, they said the standing waves happen at every half wavelength.
Okay.
And the second thing that they did is they multiplied by 1/8. Yeah, that's the article.
Okay. Well, let me have a look then.
Yeah.
So, and they got the same result, right?
Yeah, they got the same result we did. Yes.
Okay, so yeah, it must be counting the same modes, but in a different way. But yeah, thank you for, let me have a look at that, okay? I think I've seen that way of doing things as well. So it's not like, yeah. This is, yeah.
Well, actually, my question was that I'm actually curious what we did versus what they did and why we got the same answer. Like, we
Okay, so basically I
did
have to
something
look at
else that
that
was
first.
canonical, right? Yeah. Yeah, I got it.
Yeah, so I'm not sure. Okay, deriving the Arala genes from, okay, yeah, they did half. Okay, I'm just quickly having a look. Wave number. Yeah, I think, from just looking at it very in a cursory way, I think what is happening is that they are just, so for us, the wave number is both positive and negative. And if you, yeah, exactly. Sorry, let me have a look at this and get back to you in the next class. I think that would
Sure
be the
thing.
best policy. Okay. Okay. In that case, let's start with our second lecture. So, very quick review, just one line almost, is that in the last class, we derived the Rayleigh-Jeans formula. So what is the Rayleigh-Jeans formula? It gives me the radiation density around the frequency nu in an interval d nu, and it's given by 8 pi nu squared kb t divided by c cubed d nu, where the factor kbt came from the equipartition theorem. And the fundamental assumption that goes into the equipartition theorem is the Boltzmann factor, and you derive that in the tutorial. So obviously, the Rayleigh-Jeans formula, let me write those words. So the Rayleigh-Jeans formula, diverges as the frequency goes to infinity. So that's why it's called the ultraviolet catastrophe. And the Rayleigh-Jeans black body radiation was an active field of research at the end of the 19th century. A lot of theoretical physicists were trying to find a way to explain this. So of course, since the radiation density diverges, the total radiation, which will be the total if we integrate over all the frequency, I should say the total radiation density, because this is radiation per unit volume, is going to be the integral from 0 to infinity of u nu d nu. And of course, this is infinity, and this infinity, the divergence comes from this n. Okay, so bad news. So how did Planck solve this problem? So the next topic that we will discuss is called the Planck hypothesis. So before we talk about what Planck did, Planck, of course, was not working in vacuum. He was influenced by other theoretical physicists who were working on the same thing. Not just theoretical physicists, experimental physicists. There were several people involved in the story who were also experimentalists. So one of Planck's friend, his name was Wien, like in Vienna. Wien had derived a formula that was appropriate, that was accurate in the ultraviolet. Okay, so this is basically opposite of the Rayleigh-Jeans formula, where It was inaccurate in the ultraviolet. However, Wiens' derivation was based on purely, it was inspired by Boltzmann's idea of molecules that is based on thermodynamics. So one of the things about thermodynamics is that thermodynamics is kind of agnostic about what is the constituents of matter, right? Thermodynamics, it makes a more general statement. So it didn't talk about, the nitty-gritty of the particles or whatever that gave rise to this radiation law. However, Wiens, so this law is called Wiens distribution law. And we don't need the explicit form of the law, but the law is U, the density of radiation at frequency nu, is given by nu cubed times some function that depends on the ratio of nu and t. Okay. In fact, this function was an exponentially decaying function. So this is essential. So we are not going to derive this, but we are going to use this. And Planck used this in his derivation of the blackbody radiation. Okay. So one of the things that Planck realized was that the divergence in the Rayleigh-Jeans formula comes from the KBT part, because you see that this part is independent of the frequency, right? And therefore, as we are integrating the frequency, we are getting more and more contribution. So from the coefficient of the of the equipartition theorem. So what Planck said, that what if it became harder and harder in some sense for the oscillators which model the molecules and the atoms on the wall of the black body? What if it becomes harder and harder for them to reach higher and higher energies if their natural frequency is large? So for the oscillators whose natural frequency is large, what if it's harder for them to reach the higher energies? Okay, so Planck said that this can be achieved if we think of the energies of the oscillator to be given by an integer, a positive integer, times some fundamental unit called epsilon. Okay, and epsilon in principle is a nu dependent quantity. Okay. So this was the idea that led to the Planck distribution. So if this was the case, this is very different from the equipartition theorem. It leads to a very different result. And let me show you how. So now we can ask again, what is the average energy of a mode? So the average energy is then going to be, say, it'll now be n times E times the Boltzmann factor, which is e to the power minus NE by KBT. And the sum now goes from 0 to infinity. So this is basically, instead of an integral where we had KBT here, we now have NE. Okay. And then we have to normalize this. So we also normalize this as we did before. So in the denominator, we have NE by KBT. So now we have to evaluate this average energy. Okay. So to evaluate this, let's introduce a new variable, x. X is defined to be e to the power minus epsilon by kBt. Okay. Then we can rewrite the expectation value of E to be, we can factor out the epsilon, and there's a sum over n goes from 0 to infinity, n times x to the power n. And that is divided by sum from n goes to 0 to infinity of x to the power n. Okay. So this is actually quite easy to evaluate. So first, start with the denominator. So the denominator is an infinite geometric series, the first term of which is 1, the second term is x, the third term is x squared, dot, dot, dot. And you know from your high school mathematics that this sums up to 1 minus x. Okay? So this is the denominator. So what about the numerator? So we can actually derive the numerator from the denominator. So note that we can derive the numerator from the denominator. So the numerator, involves sum over n from 0 to infinity, n times x to the power n. But this thing we can write as, we can factor out 1 of the power of x, and then we have n times x to the power n minus 1. I'm not going to write the limits, it's the same limit. And that we could, yeah?
Do we have any condition that x should be less than 1?
Yes, x should be less than 1, but because the exponential, is going to be, has e to the power minus, so it's, yeah, it has to be, less than 1. You're right, because otherwise we don't have that, it's like this is a Taylor expansion of this only when x is less than 1, right? So, which in this case would mean that e to the power minus epsilon divided by kBt, this is a positive quantity, is less than 1, right? So if I now take the logarithm of this, I get minus epsilon by kBt is less than, this is a negative, right? Log of 1 is 0, right? And it is, everything on the left-hand side is positive, like all these quantities, right? So it is true that this is a negative quantity. So that's satisfied, okay? Okay, so now if you come back to this, we can write this as x times the derivative with respect to x of the denominator. Okay. So now we can write this at, so when we evaluate this, this just becomes x divided by 1 minus x whole squared. Okay, we are just using this result. Okay, so then the expectation value of E becomes epsilon times e to the power minus minus epsilon by kBt, which is this factor, divided by, there will be only one factor of this guy because this guy will cancel one of the factors. So in the denominator, we have 1 minus e to the power minus epsilon by kBt. Okay, so now if I multiply both the numerator and the denominator by the inverse of this factor, then the numerator just becomes epsilon. The denominator, the first term, then becomes e to the power epsilon by kBt. Note the sign here, it's a positive sign, minus 1. And this is the average energy that we have to consider for the oscillator whose energies are quantized. Okay. So now the rest of it is we just follow the same logic as before. So before we do that, let's look at the high temperature limit, because at high temperature, we would expect more of the usual classical thermal, result to hold. So in the high temperature limit, where T goes to infinity, we find that E epsilon by KBT, we can just approximate it by 1 plus epsilon by KBT. And therefore, in the high temperature limit, this just becomes KBT, which is the result that we got from classical statistical mechanics. So in the T goes to infinity limit, in the high temperature limit, Planck's result agrees with the classical statistical mechanical result. Okay.
So for it to match the classical result, isn't T goes to infinity a weird assumption or something? Like,
no, T goes to infinity is not weird, because we are just saying that T is large. That's all we're saying. We are introducing a new energy scale, right? Epsilon is a new energy scale. We don't know what it is. Okay. Now, KBT is the thermal energy scale, right? So, which we are familiar with in classical thermodynamics and classical statistical mechanics. And therefore, we expect more of the classical result to be derivable, where this energy is dominant, right? This energy scale is dominant compared to the new energy scale. So this is a very heuristic argument, but I think what I'm trying to say is, because what is this epsilon new energy scale? We don't know, right? So it's something that is not in classical mechanics. So therefore, we want to wash it out somehow. And the way that you should wash it out is when, it couldn't, it's possible that that's not how nature worked. It could have been possible that it was the inverse, that it was somehow a very, very high energy scale, which was irresponsible. But that is not the case. In this case, the new energy scale is a small energy scale, related to the thermal energy scale. So, this is not weird. It's just like it's just saying we're taking the thermal energies to be very large.
I was considering the T with a real physical system like on Earth, where T is, not that big.
Well, but in the black body radiation, T is quite big. In experiments, it's 2,000, 3,000 degree Kelvin.
Oh, understood.
Whereas the quantization energy of an atom is of several electron volts. Okay. All right. Cool. So now what we can do is that we can now, take this nice. So this is the Planck distribution. This is the Planck distribution. We can take the Planck distribution and put it in our associate that with each mode. Then U nu d nu will be 8 pi by c cubed. So these are things we have seen before. Nu squared, but now instead of KBT, we are going to have epsilon divided by e to the power epsilon by KBT minus 1 d nu. Okay. So then what we do is that we compare this to the Wien distribution formula. So the Wien distribution law tells us that for high frequencies, this should be nu cubed times some function, which is a function of the ratio of nu and t, d of nu. So Planck said that these two things agree if epsilon, the new energy scale that he was thinking about, is proportional to the frequency, right? So, and then this we also get nu cubed here, and also this becomes then a function of nu over t. So this introduced a new constant called h, and it's called the Planck's constant, or the Planck constant, or Planck's constant. You cannot have both. Planck's constant. And the final form of the black body radiation formula by Planck is then U of nu d of nu equal to 8 pi by c cubed h nu cubed divided by e to the power h nu divided by kBt minus 1 d nu. Okay, so this is the famous black body radiation formula due to Planck. Okay, so let me make some comments, and maybe after that we can take some questions, okay? Whoa. Okay. Let me keep this here. So the first comment is, when, say, nu is small, what we have is that it's like before, right? We get U of nu is going to be, so over here, if I expand this for small nu, we are going to have in the denominator h nu. So here we'll get nu squared, right? So this is the, and this matches the experimental curve. But of course, this was never the problem when nu was small for the Rayleigh-Jeans formula. So when nu is large, then what happens is that it washes out this minus 1, right? And for nu large, this diverges, but this factor is exponentially decaying when it goes to the numerator, right? And therefore, for large nu, the Planck formula no longer predicts a diverging energy density, but an energy density that converges very rapidly. Okay, and you can compare it to the experimental graph, and it fits the experimental graph beautifully. Okay. Comment number two is that Wiens distribution law was thermodynamic in origin. But Planck's assumption was kind of statistical in nature. Statistical mechanical in nature. Okay, he was actually postulating a new law of mechanics. And what was that law? That law is the energy of a system which has, say, a natural frequency of nu is given by a positive integer times h nu. Okay? So for large values of nu, what happens is that the difference between subsequent energy levels become larger and larger. So for large nu, it becomes harder to reach the higher energy states. And in some sense, that is basically what regulates the sum. Whereas in the previous classical mechanical picture, there was no gap. So, you know, it didn't cost anything for the system to reach the higher frequencies in terms of energy. But here, there's like a bigger and bigger gap for a higher frequency between the successive energy levels. Okay, because in that case, a nu is very large. Okay. So number 4 is that Planck was well aware of the radical nature of his hypothesis. And he knew that it was a fundamental shift in our view of nature. Planck was a very, very good classical physicist, a statistical physicist, so he knew that this was something very, very radically different from what had been done before. Okay, so and he said so to his son after the discovery. He was actually quite disturbed by it. So these are the comments I wanted to make, and now I think it's a good idea to open the floor and ask for some questions. Okay.
I don't think I have any questions.
Yeah. So you wrote E nu is equal to H NH nu.
Nu.
So is H nu the function you were talking about before, a function that is dependent on the ratio of nu and t?
No, it was the exponential. This function. You see that this function, right? This function depends on nu and t if epsilon is equal to h nu, right? So, Planck derived this with his assumption that the energy of the oscillator is n times epsilon, right? But then Wien had said that in the high frequency, the energy density must have this form. And these are different expressions, because here we have a new quantity called epsilon, but this expression agrees with this expression if this new quantity epsilon is proportional to the frequency with the new proportionality constant called Planck's constant. Okay, and we see that this assumption satisfies the fact that we should get nu cubed, because then we get a factor of nu here coming from here. It also satisfies the fact that Wiens law demands that this function be a function of nu over t, because if you put h nu here, then the argument of the exponential has nu over t, and therefore this is a function of nu over t. Okay, so does that answer your question, Farhan? I think your
Yes, sir.
internet was probably not very stable today.
Yeah, it was disconnected. And this you knew d knew. So before you wrote another Rayleigh-Jeans formula, what is the new thing about this one, the Planck one?
So we are assuming that every oscillator which has some natural frequency nu, it has a it's the allowed energy that it's supposed to have is this, right? So I mean, this leads us to a completely different average value of the energy, right? Whereas in the previous one, so here, the Planck distribution is telling us, where's the Planck distribution here? So the Planck distribution is telling us that the average energy of the oscillator has this form, right? Which is very different from what the equipartition theorem was telling us.
Okay, got it.
Okay. And with the fact that epsilon is h bar nu, this means that the average energy depends on nu. Whereas if I go back to the classical equipartition theorem, then we see that the average energy can never depend on nu because Kb is a constant and T is an independent variable that we fix from outside experimentally. So the fact that this actually secretly depends on nu through this formula gives us a mechanism of regulating the energy as a function, the average energy as a function of nu, whereas before there was no way of doing that.
Okay, and on commentary you mentioned the difference of something gets larger and larger. Could you
Right.
please explain that a bit?
Yeah, sure. So the problem with the Rayleigh-Jeans formula was that it was divergent, and it was the divergence was coming from the higher frequency modes, right? So with the Planck hypothesis, what we see that the higher frequency modes, suppose we have an oscillator whose natural frequency is nu, but nu is very high, then delta E, the energy between, say, subsequent levels, say 10,233 and 10,232, so this difference is going to be very high for high values of nu. Okay, and therefore the gap between subsequent energy levels for high frequency oscillator modes is very high. And and what Planck said is that maybe when the energy difference of an oscillator is between its successive energy levels is very, very large, maybe it's harder for that oscillator to jump to a higher energy level. It's like, if you have a staircase that has very little, very short, it's analogous to, going up a ramp versus going up a very, staircase with big stairs, right? So basically, Planck, it's kind of a heuristic argument that Planck put forward to say that why it should there should be some mechanism to regulate the high frequency contribution from the high frequency modes. Okay.
So this solves the ultraviolet catastrophe.
This, yeah, exactly.
Okay.
And this formula, we shall see this. We shall see this coming from the harmonic oscillator. In fact, this is not the correct formula, as you shall see, but it's approximately the same, correct formula. Okay.
Okay.
It's almost correct. Okay, anybody else? Any other questions? Okay, if not, let me carry on. So, so what does this, where does this leave us? Where does this lead us to? So it leads us to the idea that energy is discrete, that there's a quantization of energy of the oscillator that make up the radiating atoms of the system. And this quantization of energy, the formula is E nu is given by N H nu. Okay, where nu is the, if you like, the kind of the natural, maybe natural frequency is not the correct word. I should say the fundamental frequency. Okay. Because the idea of natural frequency is a classical idea, and it's not clear whether how nu is related to that. And H is a fundamental constant of nature, a new constant of nature called Planck's constant, and it's tiny, and that's what really leads to the basic energy levels to be very small. And experimentally, it's verified that Planck's constant is 6 times 6 2607 004 into 10 to the power minus 34 meter squared kilogram per second. Okay. So this is in the MKS unit. So I should use equal sign here. In the CGS unit, this number is the same, 6.62607004, but this is going to be minus 27 centimeter squared times gram per second. Okay. So have anybody seen Stranger Things on Netflix?
Yes, sir.
Yes, sir.
Okay, so did you get the reference to Planck's constant in the last season?
Yeah.
Okay, that was funny. All right, good. So, right, so these days it's more common to use what is called the reduced Planck constant, okay? Reduced Planck's constant. It's also known as the rationalized Planck's constant, as well as Dirac's H. So, and this is, so we express the same AE, now expressed in terms of the angular frequency. It's N H bar omega, where omega is the angular frequency, and H bar is H divided by 2 pi. And it's given by 1.054571 into 571 and 817 into 10 to the power minus 34. And we can also express it as joule in terms of joule second. Okay. So one thing to note is that if you take the dimension of H bar, the dimension of H bar is that of angular momentum. Okay. So now the natural question that arises is that how was Planck's constant measured? Right? So the way that you can measure Planck's constant is by comparing it with the consequence of the Planck blackbody radiation formula with some other laws that are easy to experimentally measure in the lab. So one of them is that what is the total radiant energy? Okay. So the total radiant energy density, I should say, the total radiant energy density is U, and you just take U nu and integrate it over nu from 0 to infinity. And if you do that, then you can show that it's given 4 sigma. Sigma is a constant divided by c. C is the speed of light. T to the power 4. Okay, so I suggest that you show this to yourself. So throughout this course, there will be stuff that I will say show, and I highly encourage you to get everything out of the course to actually take the time to derive it yourself. Okay, you will learn a lot by doing that. So this law is called Stefan's law, or Stefan's law. They're all German. And sigma is called Stefan's constant. Okay, and it can be measured. And Stefan's constant is, if you use Planck's formula, it's given by 2 pi to the power 5 kb to the power 4 divided by 15 h cubed c squared. Okay, so this is Stefan's constant. So the other law that follows from Planck distribution is the maximum wavelength, lambda max, and its dependence on temperature. So lambda max times T is given by a constant. And this is called Wiens law. So this is not the Wien distribution, it's Wiens law. So what do I mean by that? So to show this, let me go back to my lecture notes, which I will post, and look at this. Okay. See that so suppose this is the typical curve of a black body radiation, but here you see there's a maximum where the maximum occurs. So there is a frequency or wavelength associated with that, and that is what they're calling lambda max. Here, lambda max, lambda max, lambda max. The value of lambda max depends on the temperature, and it's kind of a, it goes down as inversely proportional to the temperature. And what Wiens law does is that Wiens law essentially is telling you how that works. Okay, it's a hyperbola, and this constant B can be worked out from the Planck formula. It's hc divided by 4.965. So this is actually a transcendental number, so it goes on, times kb. Okay, again, I'm going to tell you to show this. Okay, so again, B is something we can measure. So because we can measure B, we can measure sigma, and all the other constants here are known, we can figure out from these two guys the value of H. Okay, so sigma, so sigma and B, the measurement leads to a measurement of H. Okay. Any questions?
Was H found out this way, or this B and sigma is a way to verify the value of H?
I think it was found out that way, yeah. I mean, I'm sure now there are different ways of measuring H, but possibly, yeah, I think that is how it was found out. Okay, any more questions? So in the last 20 minutes, let me shift gear and tell you about another historical experiment which leads to a new idea in quantum mechanics. Okay, so we will probably have another lecture after this on historical aspects of quantum mechanics, and then we'll move on to modern quantum mechanics, okay? So the next thing on our list is the Einstein's explanation of the photoelectric effect. Okay. So in 1905, Einstein wrote 5 papers, which each of these papers had a huge impact on physics. 2 of these papers, I think, 2, yeah, I think so, 2. 2 of these papers had to do with special relativity. 1 paper had to do with Brownian motion, in which Einstein gave the definitive proof that matter is made out of atoms, made out of molecules. And then one of the paper was about describing the photoelectric effect. So Einstein actually contributed directly in the foundation of quantum mechanics. And of course, you all know that 10 years later, Einstein also was instrumental in putting forward the general theory of relativity. But can anyone guess what theory or what was the Nobel Prize given to Einstein? What was the
Photoelectric effect.
Right, exactly. So it was photoelectric effect that because I don't think the Nobel Prize committee was brave enough to give out a Nobel Prize on either special or general relativity. All right. So what is the photoelectric effect? So if you shine ultraviolet light, say, onto a metal, then the metal emits electrons. Okay? So this is entirely reasonable because, the electrons are, you can think of them as somewhat bound inside the, metal. So, they're like in a bucket, right? They're in some sort of potential well. And when the electrons actually absorb the radiant energy, they get some energy and they escape. So this is not puzzling. But what was puzzling was that the maximum kinetic energy of the electron, of the emitted electron, was independent of the intensity of the light but it depended on the frequency of the light. Okay, so this is not something we expect from classical physics, right? In classical physics, if we shine a brighter light, what are we doing? We are giving more energy to the system. So we would say that, okay, if we increase the intensity of light, the electron's maximum kinetic energy it can get should increase, right? Instead, what happens is that, when we increase the intensity, more electrons are produced. More electrons are emitted, okay? So the energy that we are providing seems to be distributed amongst more electrons rather than being concentrated in 1 or 2 electrons. But each electron, it seems like they have a maximum capacity for absorbing the light, the energy of the light, which is dependent on the frequency of the light. Okay? The other thing is that the energy, or the maximum energy, I should say, of the emitted electron depends linearly on the frequency with a proportionality constant minus W, which is called the work function. So if you plot, so this is a maximum energy. So if you plot the maximum energy of the emitted electron, okay, then as a function of nu, then what you get is that you get a line like this, okay? So here is, there's an intercept here, which is minus W. But this is the data point. The data starts here. Okay, so how do you explain this? Because classical physics tells us that the more intense, you can think of the W, that's natural, right? It's you can think of the metal as some sort of a box, a well, a potential well, and we have filled it up with electron, and you need a threshold energy W for the electron to jump out of the box, right? And that W is called the work function. But classical physics tells us if you have a light that is more and more intense, the kinetic energy of the electron is going to be more higher. But here we see that there is a maximum to the kinetic energy. So the way Einstein proposed to solve this was to say that he said that the energy that the electron can absorb from the light has to be proportional to its frequency. So he said that each quanta of light, that the light actually carries energy in packets of h nu. So if I have some light coming with frequency nu, then we can think of it as a quanta, as a packet whose energy is h nu. And what happens is that the electron can actually absorb either the whole packet of light, or it cannot absorb it. It cannot absorb half of it, okay? That's what Einstein proposed. So if you think of it in this way, then the electrons which are, say, on this level, on the highest energy level inside the metal, when that one absorbs this light, it's going to come out, but it's going to have to work. It'll have to spend W of its absorbed energy into getting out, so that the energy of the outcoming electron will be h nu by W, and that is going to be then the maximum energy of an emitted electron. If the electron is coming from more inside, then what happens is that it'll have to do more work than W, and therefore its energy will be less than E max. Okay, so this is how Einstein was able to, explain the photoelectric effect. Okay? So what is new here? So this is reminiscent of the Planck formula. But here the interpretation is very different. Here, what Einstein is saying is that light comes in packets or quanta of energy, or light is, energy which depends on its frequency. It's up to h nu, okay, where h is Planck's constant. So, the slope of this curve is the same as Planck's constant. So later, these packets of light came to be known as photons. Okay. Light quanta. All right. So this is photoelectric effect. Do we have any questions? Oh, let me show you the apparatus that was used for the photoelectric effect. Okay. So what they did is that they had a vacuum chamber. Sorry. So you had a vacuum chamber like that, and inside the vacuum chamber, you had a cathode and an anode. And you had a retarding potential. So there was a battery. And then what you did is that they shined ultraviolet light on the anode. And then, sorry, I didn't want to, okay, maybe arrow should be like that. And when it hit it produced electrons, but then the electrons would basically, if they reach here, they would get absorbed. And then what they did is that they changed the potential that were applied across the two, the anode and the cathode. They started at a negative potential, okay? So this was a retarding potential. And what happens is that, for a certain retarding potential, there was no current. And so the electrons which had exactly the same or a little bit more energy than the retarding potential, so this is the retarding potential, they would be able to reach this other, they would be emitted here, the emitter, and they would be able to get to the absorber. And therefore, they would be able to contribute to the current. Okay, so by doing that, they can you can measure the work function. Okay, so the work function is essentially given by this times voltage times the charge of the electron, EV, right? And then when the potential becomes positive, of course, the current, there is no resistance to the electron getting emitted, and therefore, you get the current, steady current. So this is how you measure the work function, okay? Okay, so any questions?
I didn't get the part about when it becomes positive, there's no longer any resistance to the steady current.
Yeah, same.
Oh yeah. So when it's positive, then the electric field is in that way, right? And therefore the electrons, and this is a vacuum chamber, so the electrons just flow. Whatever electron is produced here, they flow very easily. Whereas when the electric field is in the opposite direction, then the electrons which are produced here, they get reabsorbed. So they don't contribute to a current. Only the electrons with the very large, the largest maximum kinetic energy can make over here. But they can only make it over here as long as the potential difference between these 2 points is is smaller than the work function divided by E, right? And that's how you find the work function, right? Where the current actually goes to 0.
Got it.
Okay. It's a clever experiment.
So what is the use of the battery, and would the photoelectric effect work without the battery?
Yes, of course it would work, but you wouldn't be able to measure the work function. The battery controls the strength of the electric field and the direction. So it's actually a kind of a, a variable battery.
So the battery is used to measure the electrons flow, and from that we find the work function.
Well, no, you have an ammeter here which measures the current electron flow, but the battery is used to produce the electric fields. So there's an electric field here, right, between the anode and the cathode, right?
Yes.
And the battery produces that electric field and controls its intensity and direction.
Okay, understood. Thanks.
Okay. Anyone else? Do you have any questions?
No, sir, not yet.
Okay, so I will post this maybe tonight. I probably won't be able to do it tonight. I'm very busy, but tomorrow, of course, by tomorrow. Okay.
Okay, sir, by the deadline for the pop quizzes for this lecture, will it be until the next class?
Was it? I forgot. When did I give it? This class or next class?
Usually, the way it happened before in the StatMe, it was like when you post the lectures, the pop quizzes we get a deadline until the next class. So I was just asking if it.
Yeah, I'm not very
until the
particular
next
about
class.
that. I will change the deadline. And also, as I said, there was a mistake in the pop quiz, so I will fix that.
Okay, sir.
And thanks to everyone who pointed it out to me. Okay, any other questions or comments?